just a little bit on invariance of the NLE. One thing I want to just make a note of before we even go through this is if I write down f of x given, I'll say 0 is mu, just to take our attention away from it, and I've got some variance right here, I can write out this formula like this. I can write it like this. I choose to write it like this with the sigma outside. I think that would be advantageous for just describing what's going on. That's a 0, so that's just squared over sigma squared. So that's my sampling distribution, that's a normal right there. So if I actually pick the value for sigma squared, I think I picked 5 last time, I could have just tucked this right in here, sigma squared, and made that a 5. And I could have made this a 5. And that's some equation. And what's random in that equation is x. So I didn't change the distribution at all. And ultimately, everything that's random is still random. It's just x. This is the same equation right here. 1 over square root 2 pi. Instead of writing it like that, I'll put my sigma squared. I'll write it like this. Sigma squared 1/2 inverse, just like that. That's the same equation. E to the minus, I'll write it down, sigma squared inverse. That's the same equation, divided by 2, x squared. So I haven't changed anything. So instead of talking about, and I'll write it like this if you like, 1/2 minus 1 to the 1/2, that's the same thing. So I haven't changed anything there. So that's the exact same equation. So if I ended up picking sigma squared is equal to 1 over phi, or phi is equal to 1 over sigma squared because the equation is invertible. So that's an invertible transform, 1-to-1 function. So I can just map back and forth. I tell you what sigma squared is, you know what my phi is, and vice versa. I tell you phi, you know what sigma squared is. So I can just replace all of this. So sigma squared was 5. This thing is equal to 0.2. So that's what phi is. So I can just go back in and replace and substitute all of this with 0.2. And that's the same equation. So I haven't changed anything. It's numerically the exact same thing. And so if you understand that concept, you understand the proof of invariance of the NLE. Is I can just write it one way and rewrite it a different way. So it's the exact same thing. What's random right there? X is random. This is the same sampling distribution. And what do I have to do to write down in terms of a function without plugging in actual numbers? I can just write this thing down right here, likelihood of sigma squared, given x. And I can write down this equation like this. 1 over root 2 pi, you already know that that's superfluous. I can just get rid of that. It doesn't help us. So, and this is going to be, I'll write it like this, sigma squared e to the minus 1/2 x squared over sigma squared. And this is equal to 1 over 2 pi. This is going to be phi to the 1/2 square root e to the minus phi over 2 x squared. So those are exactly the same equations. So I didn't change anything. So you write it one way, I decide to write it a different way. And they're the same sampling functions. So the book, what they're doing in all of this is they're giving us a little bit of notation right here. So they're saying this is the likelihood function for phi given x, and they're saying that one is the likelihood function for sigma squared given x. One of those they put a star on in the proof, but ultimately it's the exact same function. So I'm just kind of defining how I write the function just a little bit different. And so you write it down one way, I write it down another way, we're still talking about the same normal distribution. So if we built a likelihood function out of this, we'd get, if we tried to maximize it, we'd get the same answer. So same sort of function. Keep in mind likelihoods, when I transform them, I don't need a Jacobian. You only need a Jacobian when you're going to integrate over that space and you need to upgrade everything to a random variable. So really basic concept right here. So let's just look at the proof in the book again. So they're saying theta hat MLE is equal to the arg maximizer over theta likelihood written in terms of theta. I'll just give us a little bit of notation. I usually almost never do this and write that down there, but since they use a star, I want to be specific about what that notation maybe means. Then if I end up transforming, I'll say G of theta is equal to eta, then eta hat MLE is just going to be equal to G theta hat MLE. So that's going to be the arg maximizer. I can end up writing this down, arg max on eta of the likelihood written in terms of eta, but ultimately this likelihood function is exactly the same function. Really, it feels and looks the exact same. But instead of talking about theta, I'm talking about some function of this. So I'm just going to write this down in terms of eta. And if you want an example of how I'm just substituting all the notation, here's one on the board. So sigma squared might be my theta, and eta is my phi. So that's the result. And really, if I'm just kind of looking at this, if I ended up maximizing over this equation right here, the way I like to think about it is I can kind of move sigma squared around. So whatever this variable is, sigma squared, so I'm thinking of that as a parameter itself. If you want to call that v, call it v. But I'm not taking an operator over sigma, I'm just talking about this variable sigma squared. It's a little bit different. If I wanted to maximize this, I kind of just budge the sigma squared around in its valid range, so any positive value, I kind of search over that thing, and I can kind of do a line search and just find the maximum. And I can do that by incrementing over sigma squared. I could also do that by moving around the phi and try to maximize this thing. And if I'm moving around phi, what I'm really doing is I'm moving around 1 over sigma squared. So I'm just budging that thing around. And so I kind of like to think about gears, like just because I like gears. I learned how they worked when I was like 2. So some people still don't know how they work. But basically, I can either put a bicycle into one gear and pedal at a certain rate, and it'll propel the bicycle forward at some rate. Or I could put it into a different gear, and I have to just turn the pedals maybe either faster or slower to propel the bicycle at the same rate. So it doesn't really matter. They're equivalent to each other in some sense. It's just the rate at which I am turning everything. So really the only thing that changes is if I'm budging around sigma squared, it's effectively budging around phi, but at some different rate. So if I increment sigma squared at units of like 0.1 or something like that, and I bounce around on some grid like that, it'd be like bouncing around some other grid on phi space, and that grid would be just changed a little bit. But ultimately, I can still maximize the equation no matter how I'm thinking about this. So here's the 3-line, very simple proof of this. If everything is invertible. So if G is a 1-to-1 function, basically gives me the ability to write down eta inverse. And in terms of a proof, since I can write that down, everything gets really simple. And so what I might do is I might look for the likelihood function on eta, defined on eta, although I would say the parametric form of the equation is exactly the same no matter how we parameterize it, just like in this example. So I might be looking to maximize this. I'm not writing it down in terms of arg max, but they're the same process. If I maximize the function, I can tell you which argument maximizes the function. So I'm just going to dwell on the maximum of that thing. And I think the book just plugs in eta hat into this. But ultimately, you would find eta hat and report it as an answer if I asked you for an estimator. So what I can do instead of just turning eta to figure out what the maximum is I can rewrite this function in terms of, I'll write it down in terms of theta and use that parameterization, and I would end up plugging this function in for theta. So where I see thetas, I just substitute the G inverse. So if you're doing a transformation of variables, this was 1/2 of the problem. You also have to do the Jacobian. You don't need to do that for a likelihood function, because a likelihood is just rewriting the sampling distribution as a function over the parameter. So we're really thinking about the form of the sampling function. And I can rewrite that right over there where I can maximize this equation over eta. So I can kind of turn that little eta, and effectively that's going to turn G inverse eta, which is going to turn, or move, if you like that word better, theta. And so, which is equivalent to maximizing over theta. And I can rewrite this in terms of theta space. And what does theta mean in this equation? It means G inverse theta. So there's this one-to-one connection. So it's really not a complicated concept. This was true for any maximization problem you've ever played around with. I think people think this is some sort of magical result, but this has always been true. So I can rewrite a parameter a little bit differently, and I can optimize over that. So in this example, so long as phi is 0.2, that's equivalent to the MLE, which is 5 on sigma squared space. So a lot of people get hung up on the non-one-to-one example. Let's just kind of think about this. Let me just rewrite a slightly different example and think about maybe G sigma. So instead of thinking about sigma squared, maybe I originally thought about sigma, and I wanted to optimize over that. So if I rewrote this equation like this, sigma, I'd have some sigma to play around with, and I could kind of spin that sigma around and spin that sigma around until I optimize the function. And if I were writing a code and I was searching over a grid for the maximum, if I ended up defining that grid with like 0.1 length between the grid, the grid spacing would be 0.1. If I use that same grid spacing for sigma, or sigma squared, I would probably get a slightly different answer just because numerically the grid doesn't match up exactly. If I had an infinitely fine grid, then I'd probably get the same answer. So if I did something like this, sigma squared, that's a non-one-to-one transform. So if I ended up wanting to find the inverse of this thing, so I might end up sitting there saying, if I did this right here, and I try to invert back, I'm going to have the plus or minus roots over sigma. So I have both of those. So if I gave you 5 and I wanted to map back to the square root of 5, I'd be giving you the square root of plus or minus 5. Sorry. Plus or minus the square root of 5. So our third grade teachers wouldn't be appalled, or not appalled that I switched the order on that. They're not switchable. So one of those roots is valid. So if I try to plug in minus square root of 5 right in here, what would this likelihood of sampling function evaluate to? Yeah, you say negative, I say 0. So because it's not in the bounds of support. So I have to write down that sigma is positive here. So I would end up truncating and saying, no, that stuff is 0. There's no likelihood value there. And so you would need to be a little bit careful if you're writing a piece of code to try to plug this thing in. You'd probably want an indicator or an if statement to check this so you didn't plug something in. Obviously, if I plugged in minus square root of 5, I'd get a number back here if I plugged it into this function, but that's not a valid expression. It can't be negative. And so that really should be 0. So I need to adhere to my bounds of support. And so really you're thinking all of these functions have an indicator in front of them, making sure that you're in the bounds of support. So it'd 0 one of those likelihoods out. If I plugged in the square root of 5 into this, that would evaluate to something positive. And that would be greater than 0. And so that would be the likelihood value. So this is the definition that they gave you in the book. So if G is not 1-to-1, we're going to define, I'll say, the maximum on theta such that G theta is equal to eta, likelihood on theta x is equal to the likelihood on eta x right here. So we're just going to make this definition right here. So instead of inverting the function, I talked about the thetas that map to this. So this is a funny way of writing the inverse function. And if that inverse was 1-to-1, there would be only one value that maps to eta, and I would select that value, so the maximum wouldn't do anything for it. So just in terms of what we did last time, if I were maximizing over the plus or minus square root of 5, one of those would have a higher evaluation than the other one. So one of those would have been 0, and one of them would have given me something positive back. And so we're maximizing, so what else should we take as the definition of to map back? So we just take the maps over the set.
Yeah, I have a question. Does it mean like maximum likelihood of made overlaps instead of just
You have a problem with it?
It's the first one.
This one?
Yes.
No, it's not the maximum. It's just the definition of the likelihood value.
Okay.
So it's just the definition for the likelihood, not the maximum of that likelihood. So we'd have to take a max over eta if I wanted to maximize that. So it's just telling me what likelihood this is right here. So there's only one value it's going to map back to. So we just change our proof a little bit based off of this definition. So I've never asked the non-1-to-1 proof, but it's pretty easy once you see all of this. So I want this thing. That part looks the same. Maximum of eta, likelihood of eta in x. Clear? That's eta. And then I end up wanting to do this. Maximum on eta, and then I'm going to take this maximum, so I'm going to replace this function right here with this new definition right here, and I'll maximize over that. I can't invert this, so I can't even write down what that means. So, but maybe I have a definition on the board that I can use. So this is going to be the maximization over theta, given g theta is equal to eta. So it gives me the set of thetas that maximize this right here, likelihood on this thing, and I'll just write this out as theta, given x. So before I just shove that thing right in there. And so I'm just going to call it theta, and I'm going to maximize over that set. So now I'm taking the maximization over theta. So in this right here is just the max over theta. So the only part that changes in the proof is that middle line just by substituting this in. But which one do I take? I check all the values that it maps back to, the non-1-to-1 mapping. So it maps back to a collection of values. I plug them all into the likelihood and I see which one is bigger, and I take that one. And then I maximize over the eta that maps to that. So that's how you do it. But really, it's just think about this example a couple different ways, and that's what we're talking about. So every time I see a proof I don't understand, I just go to the example, build an example, and I go, oh, it's obvious. And here's what the notation means. So after I understand through an example, things become obvious to me, and then I understand by pairing it with notation. I go, oh, I see what they're trying to express. So this isn't a super complicated concept. I think people just maybe think that it is for some reason. Hopefully I've dispelled that a little bit. Cool. So there will be problems on midterms and finals where I ask you to find a maximum likelihood thing in one parameter space, and then I ask you to transform that and do it again. And if you've done the first part right, then you just plug everything into the function and you're done. If you maximize both problems, you'll spend a lot of extra time. Sometimes it's easier to maximize in the transform space and go back and do the other part first. So sometimes I make the problem a little bit trickier, that part A, when I ask you to maximize, it's probably not the easiest maximization problem to do, but in another parameterization it is. So you can probably do part B and then do part A. That's if I want to be dramatic about the devious level. Hopefully you can recognize it. David?
If we transform, maximize, then go back, then we really do need invertibility, don't we?
Say it again.
If we transform, maximize, and then transform back, then we really do need invertibility, don't we?
Yeah, well, you would need to either define your invertibility here to do it, but I probably won't give you something that's not one-to-one on a midterm. So you'd at least be able to map back to at least what the valid parameters are and easily recognize the max in that set. So I don't think you need it. So you don't need it anywhere on any of this. But probably I'm not going to give you a super hard problem where it's like you're drawing things and trying to figure out what the inverse looks like. Dylan could do it. He's really good at graphing functions in his head. So, but most of us aren't that great. Anyway, I think that's enough about that. So this is really an easy result. We like to test on it. It's guaranteed I'll test on it at some point during the class. Let's do some Cramer-Rao. Let's motivate a little bit. So there's a few motivation problems in the book. So these are right from your book. So I'm going to skip the normal example. So the normal example shows you that the MLE for the variance is a much better estimator than S squared. So I'll just point this out in the book, and you probably want to read through this. In the book, they've got X's are coming from a normal distribution. If you'd like to plug mu in there, that's fine. So the problem concerns just the sigma squared. Yeah, I believe you. So I did it when I was an undergrad. So this is really the undergrad level sort of problem in the inference class. So I believe you. So, okay, tell me what you know about this. So expectation of X bar. What's that? No. Yeah, exactly. Where did that come from? You're anticipating the next one. Expectation of S squared. Sigma squared. Right in there. Variance of X bar. Thank you. At least you're consistent. What's that?
2n minus
2n minus 1? Sigma to the 4 somewhere. How are we doing? There's something in the denominator. It's squared, do you think? Something squared?
okay, 2n factorial.
N factorial. Why not?
2 sigma squared by n minus 1
Yeah, I think n minus 1 is
divided by n minus 1.
squared. I want to say it's squared.
You want to say it's all squared?
Yeah, the whole thing.
That's the answer.
Yeah.
So this is it. So something you could verify. I probably wouldn't ask you to do this on a midterm too. This is probably some undergrad stuff. Maybe you did it last semester. If you haven't done it, throw it yourself and work through that calculation. It's a bit messy. So we could just kind of take this as something that maybe we know. We could find the sigma squared MLE. And this is going to be sum of the xi's minus x bar squared divided by n, which is just n minus 1 over n times s squared. So stuff that we've all seen. We could check the bias of this. There's a little bit of bias in there. So if this one is unbiased, then that one is biased, and here's the bias factor. in all of that. If I take the variance over that, that gets squared out, and so I can figure out what the variance looks like by using this formula right here. So I can find the variance of both of them. I could look at the MSE, which is equal to the variance plus the bias squared. And you can work through this example, or you can go back to your undergrad textbook, because this one is in all of them. So, and you could figure out that the MSE for sigma squared MLE, and really all this is right here is just this. MLE minus sigma squared, all squared, is this thing is less than the MSE for F squared. So you can work through that and you'll get an expression, and it's true, it's always smaller. So why do we ever use S squared? Because people just decided to muck us up. So a long time ago. It's an easy concept to explain. And the psychological rationale of it being biased, we all fell for it. So we also know that if we ended up wanting to transform this or anything like that and put it on sigma scale, so take the square root, that's a biased estimator. And so none of us stopped to ask about that. Well, if biasness was so great, and why don't we just use the MLE? It's a better estimator. I will point out, it's not necessarily the optimal estimator in terms of MSE. There is another estimator out there, but I will say it's the optimal, well, it's at least better than this. So this one is not even the best estimator out there. And I'll kind of point you in the direction, sometimes I ask this question, that we know what the sufficient statistic is, sum of the xi's minus x bar squared. So we know we're supposed to be using that function to estimate the variance, and we could either figure that out through the factorization theorem or something else. So the definition of a min sufficient statistic, David.
Maybe one way that, I don't know this, but this is just speculation. One reason that they might have that square is, if you think about an example where, say, n equals 1, it seems if you're going to do the NLE, you're going to get estimated to be 0, and it seems clearly silly.
I see. So they put it in as a prevention for doing something silly. So
maybe
it's like,
just like, oh, if you look at that extreme example, you can imagine where you might think it's helpful.
I kind of get that. I kind of get that you have no business estimating the variance if you only have one data point. So how would you know anything about the variability? And I agree with that. But using a silly argument to demonstrate something that's silly is probably also silly. So silly squared. Anyway, I get your point. So maybe, I don't know, I'm not sure what all my teachers were thinking. What I really think happened is they read it in a bunch of books and decided not to go too deep into things. And they're like, I don't know, this has been done for 100 years, so I'm going to do it too. I think that's probably what happens. Anyway, it's not that big of a deal. If you've been using n-1, I don't really care. So if it makes a big difference in your analyses, we got big problems.
It's big, who cares?
Yeah, exactly. If n is even moderate, who really cares? So I might ask you to come up with some function C. What would I multiply this by to end up optimizing MSE? So what you would end up looking at is the expected value of C times sum of the xi's minus x bar squared minus sigma squared. I'll square all of that. So it's MSE, so that's MSE, and I want to find C such that it minimizes this. So it's a calculus problem, and everything's squared out in this problem, so you can do calculus on it. Take a derivative with respect to C, set it equal to 0, and solve for it, and you'll come up with a different answer. And that's kind of interesting. I didn't know that until I started teaching this class, and then I paid attention to that problem, and I'm like, there's another thing we could do that wouldn't make that much of a difference. But maybe even the MLE is not the best answer. You know, the MLE doesn't take into any consideration what is the loss function. So it doesn't know how you got there. So all of it tells us, really the likelihood function is that we should be using something like that. Otherwise, we're probably going to get vetoed. What do we do with it? Which c do we multiply by? It probably has to do with even the norm right in here. So how we measure our losses. So a lot of times, it depends on how you want to penalize yourself if you're going to be wrong. And so we always have to impose this extra penalty. And I always think to myself, are those natural things, or are they just things that we're coming up with for convenience? So there's an arbitrariness to some of this. Some of this stuff we just do for convenience. I would say if you're working in a normal example and you think everything's normally distributed, using the squared error norm is natural because it appears in the sampling function. We see that squared error measure that pops up in there. And so that's probably something that's reasonable. But if you had outliers and you didn't think things were actually normally distributed, you might jump into some other loss function. So there's no correct loss function. So there's just loss functions that you can maybe convince people of make more sense in the context of the problem. So when we talk about optimality, we also have to make choices along the way. And so it's optimal with respect to what. So you can ask yourself these questions over and over again. Did I just do this for my convenience? Is there a better answer for this problem? And keep having conversations with that. And sometimes you'll end up saying, this isn't the solution to the right problem, it's the solution to some other problem. And it'll give you the advantage to come up with new solutions. So, and I think that's a great thing. So we can come up with new solutions, and it depends on what we're actually doing with our answers. I don't think AI will ever have a leg up on us, but humans are pretty flawed. They have a hard time having conversations and thinking their way through what's important in the problem. So some people like to default on the word optimal because they don't have to make any choices, but I assure you, you do. You have to come up with the criteria you're optimizing. So have a look at that problem in the book. That's probably a contender for the midterm, is pick C for me that minimizes MSE. That'd be an easy problem to ask, an easy problem for you to practice. So an easy problem to grade. So far, I think that's a good question. I haven't written the exam yet, but I promise I'll do it before Thursday when we do our yes, no, maybe session. Okay, let's just look at another problem. Say xi's come from a Poisson distribution. This is also in the book. So just as a reminder, I'll write it down like this. Probability of the xi's given lambda to the x, e to the minus lambda over x factorial. The x's are counts, so they count things. And lambda is positive. So I'll be polite and write all that down. Everything's IID here. So we know that the expectation of x is equal to the variance of x. Those are both equal to lambda. What it basically is saying that as you start counting stuff, you're bound to make errors. As the counts go higher, you're about to count things with more and more errors. And I think that does make sense. That as the number gets bigger and bigger that I'm trying to count, my variability in the counting process probably shouldn't go down. You know, I can basically count things up to about 5 or 6 just off of sight. And after that, I have to start counting things, and I make mistakes all the time. So we're probably inclined to think that the variance should be at least as large as the count may be. And I would say that's actually a necessary condition if something's going to come from the exponential family, but I'll just kind of leave it there. So if you ever see that the variance is less than the expectation and you're looking at a count, what you probably have is a mixture of Poissons. So how would you estimate or model and do everything with a mixture of Poissons? You'd probably use the algorithm, something like that. So another place where you can kind of use some tools and combine it with some theory. So we know that we could come up with a couple different estimators. So here's one estimator, x bar, n, sum of the xi's, overhead. Or I can come up with another estimator. I can do this. Divided by n minus 1, if you will. So I'll use a clumsier estimator because it's unbiased. So I might be thinking about, I want estimators that are unbiased. Personally, I don't know why I would want an unbiased estimator, but everybody insists that I should want one because it sounds good. So if I ever said something to somebody, I purposefully bias my estimator, they'll start freaking out on me, even though they don't know any math. That's what they should be freaking out about, is you gotta take an inference class and know why I would do that. That's the bias variance trade-off, and that's what we're seeing in this example. I can come up with two estimators, both of them are unbiased. So both are unbiased. I might be thinking about the L2 loss function, i.e. MSE. Why? Because convenience. So that might be one reason why I choose that. And so if I know I've got two unbiased estimators and I want to compare them, there's only one thing to look at, and that's the variance. If I were looking at a different loss function, I'd need to define what that stochasticity is, how it varies. But it's not variance, it's something else. So, but both of these are unbiased, and the question is, which one has lower variance? And we could end up looking at these expressions. You could substitute into this expression sigma squared, in this example, would be lambda. So all these formulas that we have in the normal example do lend themselves over. I could just substitute in lambda for my sigma squared, the variance term, and have my expected values for both of these. And I could analyze, I'll say this, you don't need to memorize this. If you need to know what it is on an exam, I'll just tell you what it is. So my experience is everybody seems to forget it, so including myself.
Is that formula only if it's normal?
It does work for this.
It does, okay.
So which one has lower variance? We probably have some indication on the board of which estimator is better. So somebody give me a reason for picking one of these estimators over the other without doing a ton of math. David?
The sample mean sufficient statistic, so everyone.
Yeah, I think so. So this is sufficient. We need to fill in some details right there. I could also say I have kind of shortchanged completeness. I have told you something about that if that's a complete statistic and minimal sufficient, the Lehman-Sheffield thing tells us it's unbeatable. So we haven't covered that, and I'm not about to in this class. So there are good reasons to maybe invoke completeness. It's sometimes we want some theory to try to come up with what our best estimator is, our minimal variance estimator, but we have another tool in our back pocket for this problem, and that's called the Cramer-Rao lower bound. So we're going to be walking through it. I'll tell you what it is in a little bit, and then later on you can take an advanced inference class and learn more about completeness. So that's one of the parts that I'm kind of just tucking under the rug. So there is a way to talk about best estimators. If they're complete, there's no ancillary statistic. I can't come up with two estimation approaches that have all the same properties. So in a nice problem like this, there is a best estimator. So if you're interested in more of that, you need a more advanced class than this one. So this is sufficient, and so I probably am inclined to think that this is a better estimator. Of course, I could have done something crazy and multiplied by this by some k, some crazy value, like 10 billion. It'll definitely mess everything up. So you need to be a little bit more careful than just saying, well, it uses the sufficient statistic. But at least it's using the sufficient statistic in a reasonable way here. And so I will tell you, if you're not using the sufficient statistics, you can be beaten. So, because they're the things that have all the information about the parameters. Another estimator that I could pick, and this is what the book has you focus on, is I can take a linear combination between these two estimators. So I'll say P is a number between 0 and 1, so this is just a linear combination of these two things. This is also an unbiased estimator. So it's unbiased. The whole thing. And so it also has some variance in there depending on what I pick P to be. And so there's an infinite collection of unbiased estimators, is kind of what they're pointing at. And you can always do this for a lot of problems, is come up with large collections of unbiased estimators. So being unbiased isn't really the name of the game. It's also trying to get that estimator close to the truth. And that has to do with variability. So the question is which one of these is better? What we could do if we work through everything is I could work through the variance of both of them and just compare them to each other, and I might ask you to do things like that on midterm 2. But then I might have a deeper question, and I might be asking, what's the best estimator? Is there any estimator that I just know nobody could beat me with? And the answer to this question is yes, we know what it is, and it is this estimator. So that's what we'll try to show. So let me just tell you what Cramer-Rao is. So Cramer-Rao, if I could have like one old school result in all of statistics, I like to think about if I just could like come up with something that I didn't come up with and get all the credit for it. I like this one. So I think this one's pretty cool. So it's also super simple. So the proof isn't that long. I kind of like it for that. I like the mechanics of the proof. So look over at the proof of this and we'll go through it next time. But I really like this result. I think it's super useful. It's not applicable to every problem out there, but it's applicable to the problems on the board. Cramer-Rao says this. So there's a few if conditions. So we need to adhere to these if conditions. So these are important. So I'm going to say if the expected value of Wx, the derivative with respect to theta. So I'm going back to my original sort of notation. Theta is the parameter that we're interested in, so that's the parameter of interest. So in terms of the Poisson example, that would be lambda. And x is just my collection of data. So I got all of my x's coming from some distribution. I'm going to eventually invoke something about it being IID, but let's just hold off on that. Things don't necessarily have to be IID for this to work. This formula works. So I take the expectation over this thing. If I take the derivative of this, if I take the expectation of the derivative and it's equal to this, Wx, f of x, given theta, dx, if these things are equal to each other, I can apply the Cramer-Rao form. So I want to just point out, all we've done right here, this condition is saying that I can interchange the integration and the derivative. That's all that this is saying. So this expectation right here is just Wx. Cap x is all of the data in this formula. So it's my vector of data. So this is the joint distribution. So that's just this thing right here. And so this criterion is just saying that I can bring that derivative inside.
So does this mean, and this is just like in the continuous case, does it always work when they're discrete? So you always interchange them?
You can't always interchange. So this is an if condition. So if I can interchange, I can think of examples where it's not interchangeable that are discrete and continuous. Let me give you one. So the uniform 0 to theta in continuous space. So theta is on the boundary of the space. So when I would be taking an expectation, I'd be having a theta on the integral. And so sliding that derivative past that is not fair game. So theta is on the boundary of the space, this equation won't hold. There are other examples. I could carry that out with a discrete example. And all I would be changing in the discrete example is changing that integral sign to a summation sign. So this is just an if condition. If I can apply this is called Fubini's theorem. So if Fubini's applies, then I can do a bunch of stuff. So for like the uniform 0 theta example, Cramer-Rao is not applicable. So I can't use that to prove optimality of an estimate. You would actually need the completeness sort of theorem to do that. So there is a best estimator out there, and I might tell you about that. But that's not the scope of the class. So if this is true, and this is a pretty obvious condition, the variance of Wx. So this is just some function of my data. It's an arbitrary function. So I'm not actually defining Wx. If you ask me what W is, I'm going to say it could be anything. So all this is really going to end up telling me is there's something I can do with the data that minimizes the variance. We'll talk about that in a second. So if the variance of this is also finite, so this doesn't happen, so it's not infinite, i.e. the variance exists. If we're going to try to minimize the variance on something, we probably should say that it exists. So this is an obvious condition. Then, Cramer-Rao says this. The variance of Wx, again, x is all of my data, this is going to be bounded by this thing. So the variance is going to be greater than the derivative of theta of the expectation of Wx squared divided by the expectation of, I'll say this. This is the way I want to write it. Log, I like to say likelihood here because it's still the same expression as the likelihood, but the book writes it in as the sampling distribution. But I'm going to be taking a derivative over this, and then I'm going to be integrating this over x. So I'm actually touching both variables right here. Square that thing, and that's what the formula says. So this is one derivative, square that thing out. So I take the log likelihood, and I'm going to be taking this expectation over x. So however you like to think about this function, you're going to be touching theta and you're going to be integrating over x. So you're treating it in both fashions. So this is a theoretical lower bound for the variance. So what this is saying is I never work through the left-hand side. I just write that down notationally. And I say, is there a function of the data that matches whatever this value is right here? I'll show you an example in a second. But this is the theoretical lower bound that might be useful for figuring out where the boundary is for being able to reduce your variance. So basically it says if this formula applies, if that condition is true, then there's no estimator of the data that can give you a variance that ducks below this value. Let me give you an unuseful bound. Maybe this one should be called Scotland's lower bound on variance. Variance of Wx, so I'm just going to say some function of the data that I'm going to use to estimate theta, the variance of that has to be greater or equal to 0. So that's not useful. We all know that. Variance is positive. So the theoretical lower bound on the variance is 0. Great, thanks for telling me nothing. So I already knew that. This might not be 0. And it's telling us that nothing I can do with the data would ever give me a variance that's smaller than that value, if this condition applies. So sometimes on final exams, I say, what does Cramer-Rao say about this problem? And everybody ends up running through, or at least half of you might run through, do all these calculations, boom, 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 and you didn't check this condition. And the answer to the question is nothing. It doesn't say anything about this problem. So it doesn't apply. So don't do any math if it doesn't apply. What we might want to work out right here, and we'll come in and we'll figure out the details of this, is all we're going to do for the Poisson problem, what we might do is we might take the derivative with respect to lambda, the expectation of Wx, squared, right here, divided by this thing. Derivative, d lambda, I need to build up my likelihood function. That's the way I like to think about it. So this will be e the minus lambda, lambda to the xi's, divided by xi factorial, squared. So I need to just work this thing out right here. So the numerator is working out the bias level. So here's how people use it. For unbiased estimators, this thing right here, if I were considering W to be the class of unbiased estimators, then it would tell us that the expectation of that thing is lambda. That's what it would mean to be unbiased. So if I were looking at the class of unbiased estimators, this expectation would be lambda. When I take a derivative over that, that's going to be 1. So I could end up looking at estimators in different classes with different bias levels, but the numerator is basically just telling us about our bias level. Chris?
There's a log in the formula of that.
Oh, there's a log, yeah. I always forget that log, so thank you very much. Log, right there. If you end up start doing some math and it turns crazy, it's because you didn't take your log. So I'm going to ask you things in the exponential family, and taking logs helps a lot. So I'm not going to ask you, crazy distributions or stuff. So I thought you said there's a lie. But that's what we end up doing. I'll just tell you what this ends up becoming. This is lambda over n. And we're going to work through this next time. I'm going to give you a couple simplifications for this formula too, so that you don't have to work through it. This would be a brutal thing to work through. If you ended up doing, you can try, and there's an easier way to work through this calculation. And that's what we'll start up class with next. But ultimately, this is lambda over n if you work through this calculation. I'll show you how to do this calculation a little bit more simply. So what it says is in the class of unbiased estimators, so where this thing is 1, so if I ended up picking this to be lambda so that this is 1, then it's saying no estimator out there can have a variance that's less than this. And over here, we've got an estimator that does that. So we know what the variance of x bar is. It's going to be lambda over n. So that's what we would end up working out. Because everything is IID. So now I have an estimator that attains that lower bound, so I'm stoked because there's no other estimator that can beat it. So there's other ways to tackle that problem, but this is probably the cleanest way to do it. So I'm going to definitely ask you a question on Friday where you're going to apply Cramer-Rao formula. I'm going to ask you, is this the best estimator? How do you know? And you're going to work through Cramer-Rao, and you're going to say that I've got this estimator right here, and it attains the Cramer-Rao lower bound. I will tell you there's also a part of the book on attainment, and it tells you when the Cramer-Rao lower bound can be attained. What it's basically doing is unwinding the proof and showing you the condition that has to be true for you to attain the Cramer-Rao lower bound. We're not going to cover that either. So I'm going to give you an estimator, and you're going to check to see if it attains the Cramer-Rao lower bound. You could probably invoke something and say, oh, it's a non-complete statistic, so it doesn't attain the Cramer-Rao lower bound. If you pull out answers like that, I'm going to give you full credit for it. They just have to be correct. So that's not the stuff I'm going to test you on. But if you do know more advanced theory and you use it, you'll get full credit for it. So I'm going to be giving you estimators and having you check to see if they attain the Cramer-Rao lower bound. And if one attains the Cramer-Rao lower bound, you don't need any theory. So it attained it. It happened. So I know that it's true. So this is one such example of that. That's it for now, you guys. We'll come back next time, finish up this example, and we'll do Cramer-Rao's proof. So have a look at that.